Hello and welcome to another one of these ADD videos. Today we're going to be talking about the concept of electric potential. If you remember talking about potential energy, we discussed it in terms of work. Well, electric potential is the potential energy per unit charge. So U over Q is what V equals. A group of charges can create a uniform electric field or just a single charge, and as a result, around that we could calculate the electric potential. So just like when we were discussing the electric field, there was no point there. The electric potential, there will be no point at we're looking at. There doesn't need to be a point. Okay. We can also have a system of charges that also create an electric field, and we can calculate the electric potential with the system of particles, and it's going to be the amount of work required to bring the system of charges into that configuration. So we can also look at the perspective of electric potential between 2 points, and notice that the subscripts, normally it's the last one minus the initial, but not here. But it's the amount of work it would take for a positive test charge to move from A to B against an electric force, or the amount of work it would take that electric force to move the positive test charge from B to A. If you want to change your perspective, if you remember from work, there's two perspectives. There's one from the system, or there's one from the surroundings. Go back and review work if you don't remember. But basically, this potential difference, electric potential difference, is referred to as voltage, and it'll be the driving force for movement and charge in circuits. Okay, the batteries that you see have a potential difference on both ends. There's a positive end and there's a negative end. All right. So what are the formulas that we can use to calculate electric potential? Well, if we just take the potential energy formula and divide it by the Q naught, we get this wonderful formula here. It's basically the U, but we divided by Q to get rid of that. Okay, K is still equal to 9 times 10 to the 9th newtons meter squared over coulomb squared. Q will be whatever the charge is, and R is the distance from that point we're looking at, field point or the potential point, to the charge in question. Now, you might have more than one charge. If you have a system of charges, of course, you can always use the vector techniques we've been using up until now to combine the components. So, multiple system of charges would be the summation from 0 to however many charges there are, each individual charge, and the distance to the point we're calculating the potential to the charge in question. The SI unit for electric potential is 1 volt, and 1 volt is a joule per coulomb. Work is measured in joules, and charge is measured in coulombs. So the other important relationships you will need to know is that the electric potential relates to the electric field by doing a product here. We've already discussed this relationship. The value of the electric potential is independent of the path taken, so this could be an integral here with the differential line segment for L if we're dealing with a collection of point charges, but using the vector stuff is what typically you will deal with in our class. You can find the electric field by using the partial derivatives. We'll look that up in a different video, as well as equipotential surfaces. Make sure you understand the difference between electric potential V and potential energy U. Alright? But that's basically it as far as an introduction to electric potential. I hope I've clarified any doubts you might have over electric potential, what it is, how to calculate it. Now, it's up to you to practice some problems. Thanks for watching, and have a nice day.